Hello, my name is Carl Cook, and I'm President and Chief Technical Officer of IntelliDynamics, a division of Biocomp Systems. And this is session 2 on capabilities in the Intellect 3 architecture. And it's basically a introductory briefing at a conceptual level. And in the prior video, we talked about data access and virtualization. And now that we have data in hand from its data sources and synchronized, I'd like to talk some about how we validate, clean, and convert it. Once again, going back to our pyramid that we saw in the first video, we are at the validate, clean, and convert level as we're building our solution from physical data stores up through data access and cleaning and converting it, moving on upwards to causality, modeling, prediction, optimization, so that we understand, anticipate, and can take actions to achieve a business benefit. Whenever you use a fact-based system, our decisions require high-quality information. Anyone who makes decisions must have high-quality information, otherwise you're going to end up or are at risk of making the wrong decision based on bad data. That is not a good thing. And we base our futures learning from the past. And so accessing past data and analyzing it and determining what the facts are and making decisions is all a part of using data-driven solutions. However, data is almost always dirty, noisy, full of invalid entries, missing data. It's in different forms. And we need to clean and convert that data and validate it before using it. And then we need to combine those values across variables to start extracting meaning from it. And of course, all the rage these days is big data, but one of the attributes of big data is that it's big. And processing lots of big data is costly and time-consuming. So we need a way to shrink it down to its essence. So we must validate, clean, and convert our data. Now, as I said, data is dirty, and that dirt comes in various forms, whether that's data entry errors, presuming that someone is still writing things down on the clipboard and typing them into an Excel workbook or a database someplace, or where in the automated systems where the data is automatically collected, there are technical problems and things happen. And sometimes you're notified of that and sometimes you're not. And even if things are running smoothly, the sensors that are being used to collect the data are oftentimes noisy. They have a lot of variation in them. And it's difficult to extract the, quote, signal from the noise. And data can be missing, just doesn't exist. Data is asynchronous, so something is entered in at 12:01 p.m. over on that system, and at 12:04 p.m. something else is entered in a different system. Let's say you have process conditions at one time, and then you have a lab test later on, less frequently. And so there's asynchronous nature to the data, and which yields gaps. And any given series, based on experience, firsthand, can contain text, nulls, messages, invalid values, and valid values, but of a different meaning in a different context. So in the example I have on the far right with the red, bright red characters in it, I just created a time series of data that is pretty typical, actually, where you have a couple of what would be normally considered valid values, and then all of a sudden in that data you get the text I/O error. This happens sometimes in some of the real-time data historians, whose names will be not mentioned at this point. And then you have another valid value, and then nothing, a gap. And then you've got something that's 10 times too big. And then you're back to normal again. And then you've got a negative 239, which maybe in another interpretation is actually a statement about that particular data series, that perhaps that means that something is happening, and so a whole value, HOLE, is written into the series, indicating that yeah, I got some data, but it was bad, so I'm going to put in minus 239. So you might want to watch for 239s and minus 239s and take them out. And then you go back to a valid value again. This is normal. This happens every day and must be dealt with. And any tool that's worth its salt is going to be able to handle this. So some of the capabilities that we provide to validate and clean it would be clipping and limiting. So for example, the 430, which is 10 times too big, presuming that in absence of any other knowledge, that is actually an error, you could clip it or limit it. Clipping would mean I'm going to take the 430 out and I'm going to replace it with nothing. Or I'm going to drop the entire row of data that has that 430 in it because I question the entire set of data at that moment in time. Or limiting might say, well, I know that this series goes from 20 to 50, and that says 430, so I'm going to limit it, and it, of course, pegs the limit at, say, 50. And also, you could do text drop, where you see the I/O error. You could drop that row of data where it says I/O error, or you could convert that I/O error into some numeric value. Let's say that you are actually wanting to know how often you have I/O errors in your data. Well, then I/O error no longer is a bad reading. I/O error is something you're looking for. So maybe you want to drop all the other values and keep I/O error. So that gets into the whole concept of outliers. Outlier is something that's not like the rest of the data in its very simple definition. But sometimes you're looking for things that are not like the rest of the data. So outlier is not only contextually based, but it's also, its meaning is based on what your objective is. So if I want to quantify I/O errors, I'm looking for I/O error. I want that. I want to convert that maybe into a number or count it. So you could convert text to numeric, and you could also do missing value replacements. And in time series, one of the things that we support, which is actually works pretty well. It's very simplistic, but if you don't know what the current value is of something, you cannot interpolate in between prior and future values, because when you're running online, the future values do not exist. So you cannot interpolate. So what you can do is pull forward the previous value. So that gap that's in there between 42.7 and 430, that might be pulled forward with another 42.7. That's the best guess of what the value should be, given that you don't have any other information. Now, if you wanted to do something more sophisticated, that's quite possible. In other words, I could estimate that 42.7 based on other columns in my data set, and then when I come to the blank spot, I can look at the other columns in my data set and estimate what that value should be, which would probably not be 42.7. So there's different ways of doing missing value replacements. And data is in different forms. It can be numeric and text. It could be text within numeric, as I just showed. It could be real-world actions, such as valves opening and closing, having text like open and closed, which actually you want to interpret as being events. Or they could be states like on, off, open, closed, running, stopped, and it could be structured or unstructured. So we have a variety of data conversion capabilities that include event detection and text to numeric and missing value replacement. And so you might want to see an on or an off, and you might want to convert that in a text to numeric to a 1 or a 0. Same with running or stopped or open or closed. If you need to do math on state variables or text, you can convert it into numeric values and then do your math on it. Also, values across variables give meaning. In other words, that a singular data column in isolation is rarely sufficient to understand what's going on in the process. It contains useful information, but usually you want to combine that column of data with other columns of data to derive some result that has higher utility, more information content. So we need to be able to apply math and logic operations upon it, such as sums and differences and products and ratios and logic processing, and y equals the log of a over b plus the sine of c minus d. If a is greater than 0 and b equals closed, then some other result. So we provide sums and differences, ratios, products, log, trig functions, hundreds of functions and billions of permutations to create an engineered data handling solution. And I'll give an example of those here in a moment. And then big data is too big. And because it doesn't matter how much data you have, it's the quality that matters. Somebody in the oil and gas industry says, so you want to build a model of estimating oil production on a well based on process conditions using well test data. How many well tests do you need? And the answer is I don't know, because it depends on how much information is in a given well test, whether or not they're manipulating the process and giving a design experiment where we have a lot of variation in the process conditions and control handles, and the oil production as it moves up and down. As they do that, then maybe only one well test is necessary, and not necessarily 100 well tests that are each at their own steady state values, and maybe just replicates of each other. So having big data is not necessarily an advantage. It may actually be a significant disadvantage because of all the costs to collect it and store it and process it and all the CPUs required to crunch it, and etc. So processing millions of rows is often unnecessary, so we need some data summarization capabilities. So either generating different kinds of statistical measures on a set of data, or if it's a time series, bucketizing it. We have something called DTR, date time reduction, which says I'm going to take everything and average it into, say, 15-minute buckets or 15 millisecond buckets or weekly buckets or whatever. And then all of a sudden, the next thing you know, you go from having a data set in your tool of 547,000 rows down to 4,700 rows, and everything goes much faster, and you haven't really, if you don't bucketize it less than you need, you haven't lost anything. You actually probably have gained not only speed and performance, but also perhaps the quality by denoising it in the same time by summarizing it. So we have a plethora of different kinds of functions. I'm not going to go through these, don't worry. But we've got ways to copy columns and time shift them and compute changes and some different kinds of moving averages and medians and mins and maxes and statistical variation over period walking forward windows and slopes and rates of change and ratios and sums and differences and multiplication and divisions and trig functions and correlations and standard deviations and all sorts of different kinds of functions that it goes on and on. We can invert, we can take the percent of change, we can compute persistence, how much something is changing or not changing. And these operate both on the desktop and online in real time. And you can add in your own as well. So within our tools, the next level above the data virtualization is this data handling, and you can create data handling templates that specify what variables to use through the data virtualization and data manager, how to process them, and you can derive high quality data or state detection or whatever application it is, and you can pre-process data for use in later analytics, or it can be used standalone as a data cleaning and conversion solution so that you can run this whole data access and cleansing and conversion scheme in real time, and is sitting there getting data, cleaning it up, and then writing it someplace on a continuous basis or on a timer or whatever. So anyway, this gives you some insights into our capabilities related to validating, cleaning, and converting data. The next video in the series we'll start looking at how do we understand what the data is trying to tell us, what information is in there that we can use to move the next step towards delivering the business benefit. Thank you very much for your time, and please stay tuned for additional videos in this series, and we appreciate your interest.